This is Computing Up, conversations about computation writ large with Michael Littman and Dave Ackley. This episode was recorded April 12th, 2021.
So I got my vaccine appointment.
Oh, great.
I'm pretty excited. I was pretty nervous about the whole thing. Not that I'm saying I'm vaccine hesitant, but I'm stabbing hesitant.
Well, there's good evolutionary grounds for that, I would think. And which one are you going for?
So I got 3 appointments. I figured that way I should be totally covered. I got Pfizer, and J&J. And then when I got the J&J, I canceled the other one. So I should actually be officially immune by the time my daughter graduates from college at the end of the month. And so I might be able to participate.
Wow. Well, that would be exciting.
It would. It would. I mean, that's the whole point of being a professor, is so you can go to your daughter's graduation officially.
Is that the point? I always kind of wondered.
Yeah.
And I got my second shot coming up at the end of this week.
Boom. All right. We're going to make it through this,
step by step. Yes. Let's. Very lucky, and it's all because of frickin' science.
Science!
And because of people doing stuff like making substitutions and base chains that nobody knew what it's good for, and now all of a sudden it's good for something.
Yep.
And all that stuff. So
I like one of the things I really like. You know what? We'll talk about this later, because I wanted to introduce you, Dave, to our guest for today.
All right.
So we're going to talk to Professor Tina Eliassi-Rad from Northeastern's Network Science Institute. So Tina is a machine learning, data mining kind of person who's applied her skills to advance the use of empirical methods in network science. Lately, she's been thinking a lot about ethical and unethical uses of AI technology.
All right.
Also, back about a decade ago, I hired Tina into her first faculty job. So I've been keeping up to date on her work, and I'm really glad she agreed to come on the show. And, I wanted to introduce you guys and have a cool conversation. So hi, Tina. Thanks for being here.
Hi, Michael. Thank you for inviting me. Hi, Dave. It's nice to meet
Tina.
you.
Nice to meet you. We were supposed to do this several weeks ago, and I managed to blow my frickin' appointment. So this is our makeup call. So thanks so much for making an extra bit of time.
My pleasure.
So excellent. So Tina, why don't you say, if you wouldn't mind telling a little bit about, we've all done machine learning research, so we have that in common. So maybe you could say a little bit about the work you've done there, and we can kind of branch off to broader questions.
Sounds good. So basically, since about, I would say 2005, I've been looking at graphs and networks. So usually machine learning people work on data, right? Some people have an affinity for text. Some people have affinity for images or video. I like graphs and networks, so nodes connecting to each other. And the idea is that there's relational dependencies. That is, the links aren't being formed randomly. So if you think about the Facebook friendship network, there's something behind why, for example, I would accept a friendship from Dave. Here, it would be through you.
Let's take a step back. So, but it seems like a graph is data in a sense, especially if you're talking about something like, I don't know, IMDb or whatever, where there's lots of information about movies, or like you said, the Facebook kind of graph. It's just a graph, but it's kind of loaded with data. You could think of each person as being a kind of a data point. So is that wrong, or is that incomplete?
It's absolutely right that each person has their own data. In fact, the reason graph neural networks are so popular these days is because a person has lots and lots of data, and now they're capturing that. But when I started, we were just looking at the network structure, at just the friendship structure. And for example, for social networks, we know that there are 2 processes that dominate the formation of a social network. One is attaching to stars. It's called preferential attachment. So when you come into a network, you want to attach yourself to a star. The second one is closing of triangles. So friends of friends is a friend, right? So you are the root of this tree that's now connecting me and Dave, right?
You completed the triangle.
Indeed. And so the more triangles you close, the better it is for a social network.
Let me see if I'm getting this. So if you can think about one of the things that's data-ish, machine learning-ish about a graph is that each node in the graph, so it's like people or cities or what have you, has a set of other people or whatever that they're connected to. So you can think of that as being kind of like a feature vector. My feature vector is the list of all people, which ones I'm connected to, which ones I'm not connected to. But it sounds like what you're saying is just thinking about it that way is not really I don't know, accurate is the wrong word, but it kind of it leaves something out, because it's not like these feature vectors are created completely randomly or IID or anything like that, but they kind of accrue because networks are formed incrementally, and the accruing process needs to be part of how we think about that kind of data.
Exactly. So basically what you're thinking about in terms of machine learning is that there's actually relational dependencies. So the fact that I'm now friends with Dave just didn't happen out of like blue, right? It happened through you, and that is important. And so since it happened through you, I can infer a lot about who Dave is. And in fact, this is a whole wing of people who work on machine learning on graphs in terms of guilt by association. It goes back when your mom would say, like, don't hang around Bobby. Bobby is a bad person, right? And like you would go down the wrong path. So it's very much like that.
So let me play Michael's role actually and sort of back us up a little bit yet further here, because a sound, an image, a smell, a touch, these seem quite concrete to me as data goes or something like that. Even saying a sound is a word is a little bit more abstract to me than just, bird call. Well, I don't know, something like that. But graph seems even a step beyond that, as far as not being concrete, as far as one has to do more abstraction, more processing, more lifting away from the sensory before you even have a notion of a graph. Like you could have a graph on top of sounds, a graph on top of bird calls, a graph on top of words, but that's not really sort of peer to peer. You see what I'm saying?
Yeah, I see what you're saying. So here's the thing. So as you can imagine, social scientists have been studying social networks for a very long time, but the way that they had looked at it was very much small data close to the people. Right. So there's this very famous data set about 14 Southern women who would get together and they wanted to see their interactions and like who was the star and so on and so forth. And so then you would know what a link actually meant. Right. Now, for example, in the Facebook world, Tina may have 1,000 friends. Clearly, Tina doesn't have 1,000 friends, right? We know Robin Dunbar.
Dave doesn't
Well, let's think about like what friendship would mean, right? So, according to Robert Dunbar, who's an anthropologist at Oxford University, our human brains are such that we can only really have about 200 friends. Friends is, for example, I know whether you're married. I know, the name of your children. I know the name of your spouse, so on and so forth, as opposed to just, like I met you once and now you're my friend, right? And so some of those notions of friendship have lost total meaning, right? So then if I, for example, take Tina and her 1,000 friends, I can't treat them all the same way, right? And that's actually where some other information in terms of graph, like how much did I like the things that you posted? Did I love it? Did I like it? And all of those comes into play for me to be able to infer the strength of my tie with you, right?
So when I think about a graph, I think about, nodes, circles, and lines. Yeah. But that's quite discrete. There's either a line or there isn't. Whereas you could put a number on it, you could put a weight on it, like what you were just saying. So that really, in some limiting case, everything is connected to everything, but something by very, very, very small values and so forth. And then it's a matter of the data scientist's choice to say, well, unless it's more important than this level, I'm going to chop it out and pretend it doesn't exist. And then the analysis can go forward.
Exactly. And in fact, one of the things that happen in social media and all the data where they make these kinds of complex networks is what I call the paradox of big data. I have a lot of data, but when it comes to inferring something about you, perhaps I don't have enough data, right? Because you are not as active. And so if you're not as active on Facebook, then oftentimes what happens is you basically get cut out, right? It's like as if you didn't participate at all because you haven't been active.
I am in the noise.
Yes.
That's my problem.
But the main thing is that there is some process that's generating this. And if I can find what that process is, then I can do better learning in terms of whether I should show you that black shawl or not, or, some other kind of an ad.
Right. Okay. And all right. So I mean, so one thing about the graph is how do you decide what's in and what's out as far as a link goes? Another thing is that in order to actually do anything with it, do you kind of have to know the whole thing? I mean, doesn't this sort of imply some kind of centralization to run a graph algorithm on a graph? You must have the graph all in one place.
So, excellent question. So there's this notion of, am I partially observing the graph, or do I have full observability of the graph? And oftentimes people assume that you have enough observability to make inferences. Though actually my group has done work in terms of, okay, if you give me a budget, perhaps I can go and collect more information to bring in more of the type of the people that you're interested in. So before the pandemic, I was discussing with a clinic in San Francisco through the CDC, where they wanted to have more of the social network of people who had sexually transmitted diseases. And so if you have some sexually transmitted diseases in the social network that you have access to, but you know is partial, how would you go and collect more data to expand your observability? So that's a really good comment. The other aspect of it is the network changes over time, right? So it's not static. And oftentimes you have a process on it. So right now we're going through a pandemic. You have connectivity network, right? The mobility network. And then on top of that, you have the virus that's going around. And so they oftentimes, for example, model it with these compartmental models like susceptible, exposed, infected, recovered. And so which state of that state are you in? And now that I've come into contact with you, depending on what that contact is it in the park? Is it in a bar? You know, how likely is it that I will change my state based on my contact with you?
I never understood why there was no dead category in SIR models.
There is actually. So in the recovered, the way that they're now modeling it, there's recovered dead.
I see.
No, actually they break it up in terms of the different
two kinds of recovery.
Recovered dead, recovered.
I see. Okay, well, that puts a spin on it.
And in fact, in terms of machine learning, one of the things which is really interesting is like, can I do reinforcement learning on a mobility network where my states are for each person, their state changes? And if I can effectively do reinforcement learning, then maybe I can effectively propose policies to policymakers, right? I can say, okay, if you do mask wearing in this county, this is the cost, this is the reward. If you do stay at home in this county, this is the cost, this is the reward. The problem is with the pandemic, the data is very bad, right? In fact, people are separating it in terms of nowcasting and forecasting, because like some of the data is like a month old.
All right, just to be clear, nowcasting is like predicting what's happening now because we don't really know.
Exactly.
Okay.
And we do know that the process is evolving. We do know that conditions are changing.
Yes, like indeed. And for a long time there, like in the U.S., the death numbers were lagging by a week. So you weren't getting accurate numbers. And this was the case in many parts of the world.
I guess... what's the aft casting? What's the third case? Now casting, forecasting, and
then
trying to predict the past. I mean, that's bad enough. I don't know if we can do that.
Let's not predict the past.
Well, I mean, it would show the repeatability issue.
Value,
like that.
I mean, the recent past wasn't very good.
So repeat, no, like that. Well, okay, so graph seems like a hugely general. If you can say something about graphs in general, you sort of, I mean, they're so general, it seems like you're going to have to make little sub something or others and say, I'm only talking about this. And again, it's going to be something about the researcher or the policy decision to decide, or the algorithmic decision, the Facebook decision about what graph to look for, what graph to look at, and what graphs to ignore, like that.
Exactly. And also there are lots of other cool issues in terms of how do you mathematically formulate the graph. So should I have it as a simple graph? Should I represent it as a simplicial complex? Should I represent it as a hypergraph? Do higher order structures matter?
All right, wait, hang on. You're losing us here. So these are all
simple
choices,
graph,
none of which mean anything. So, or not. I'm sure they mean things. They're just not meaning anything to us.
I see.
So
simple
these are
graph,
modeling decisions because So the world is what it is, and we're trying to put some structure on it so that we can do some
Indeed.
kind of computation. We want to be able to, like you said, intervene on a virus network to try to slow the spread of the virus. Something we have something that we would like to do.
Make our best bets.
Yeah, right.
Take our
Or
best
just understand things. Design our next movie so that it's going to be a blockbuster hit, whatever it happens to be. And so, but we have choices and when we're making it into something formal that we can manipulate or have the computer manipulate on our behalf. There's choices. All right. So you said simple graph. So that's like nodes and links.
Yeah, that's just nodes and links. So I'm just looking at the dyad, right? I just know that Tina came in contact with Michael, right?
All right. So a dyad is like the two ends of an edge.
Pairwise.
Yeah.
Exactly.
So, I see.
And then I could go to what's called higher order structures in general, right? So for example, maybe it's important for me to know that the virus goes from a house to a church, then to a grocery store, right? So there are people that are moving in these different parts of the world, but oftentimes the spread is house, grocery store, or church, or house, church.
So instead of the nodes being, well, the nodes could be people, and if you can think of it as being person to person spread, but it might be more useful to think of sort of group to group. And that's where you get something like a hypergraph. So a hypergraph it links subsets of nodes to subsets of nodes.
Exactly. Or for example, like if you go beyond just the dyad, the two-person, one of the things that's near and dear to us academics is publishing papers, right? So perhaps you would know that I published with you, and I would know that you published with Dave, and you know that I published with Dave. But what if the three of us published papers, right? If you just look at the dyads, then you don't get the fact that the three of us published the paper, right? Okay. And so you could try to, as you were saying, like represent it as what's called a hyper edge, where there would be a hyper edge of the three of us that said, oh, the three of us published the paper together.
Right. So it would be a line with three ends. And you could have, well, I mean, it's a line with three, a Y.
A Y, I see. Yes,
a line
good.
with three ends.
That is a line.
And you could go as far as you want.
Right.
But the combinatorics will completely slaughter you.
There's that. There's like, what is the spectra of a hypergraph, right? We rely a lot on eigenvalues and eigenvectors to, for example, to find paths, to, lots of other cool things on graphs. But the modeling assumptions that you make in terms of how am I going to model this real world phenomena that I know is complex has a big impact in terms of what on the end you get. And of course, as you increase the complexity, as you were just saying, of the representation, are you getting what you want for the money that you're paying?
So there's also there's also the point that if you wanted to do a third order model or some other higher order model, you're going to need that much more data to get anything that isn't just fitting the data. So you may be forced to do a low order model, a second order dyad thing or whatever, because that's all the data is going to support, even if it's missing really important pieces.
Exactly. And so one area of research is how do you do model selection to find the right order? Can you do model selection to find the right order? Is
there some kind of jackknife bootstrap? Do
there's
2, do 3, do 5.
Absolutely.
And it'll voila, 3.2.
Indeed. Well, you can look at it in terms of the right order per node or the right order for the entire graph.
Globally.
So people have looked at it both ways. So.
And it feels like the trade-off, I mean, there's the trade-off that Dave was mentioning in terms of sort of time complexity and data complexity versus accuracy. But there's also, I mean, I feel like it's come up a lot on this podcast is the notion of, I mean, the world is really big and complicated, and it's what Rod Brooks said, it's its own best model, but it's not a model you'd want to compute with. And so at some point you have to kind of pick, right, how cartoony are you willing to be versus how realistic you want to be. And there are trade-offs that are just inherent in this. So Tina, it sounds like you do some of your work is in terms of algorithms and testing and using maybe existing data, but some of it is getting out there and figuring out how should we think about this problem? What is the right level to model it? Do you have a process that you follow when you do that? How would you guide someone?
Yeah. So the main process is to talk to the experts, right? In whatever field that you're looking at, whether it's biology. So for example, right now I have a project on drug discovery for COVID. So therapeutics for COVID. So actually talking with biologists and geneticists and chemists to see what's the right way of representing it. So if you think about it, I have the known drugs over here as one set, right? And I have the viruses, including the coronavirus over here. So I have this bipartite graph, right? 2 modes. Now, I could represent it as, in a way, just link prediction, right? So here's a new node, the coronavirus, which existing drug would it connect to? And a lot of the data that exists is actually that. Or I can say, like, the strength of binding, right? So then becomes regression. Or I can say, which of the existing drugs is it more likely to bind to, right? So then it becomes a ranking. But then, like, getting that data to then train, do supervised learning, because all of this is supervised learning, is very difficult, because the biologists and the domain experts don't think about as, oh, this virus is more likely to bind to this than to that. Or, like, ideally give me a number of, it's more likely to bind to this at 0.9 and this 0.85, and right. And so in terms of how you represent, you need to talk to the experts.
Do you see a tension when you talk to experts, though? Because I think, and maybe this is just my friends in my graph, but I think machine learning people tend to have a bias, which is, we want the data to tell us what's going on because we don't really believe the experts. Right? We think that we're going to find something that wasn't there. So we're going to make a better Go playing program than the experts knew how to do, because we're going to, get at the real problem as opposed to people's flawed notions of what the problem is. But on the other hand, people have thought about some of these things for a really long time, and blowing them off and just saying, oh, no, we're just going to do it from the data. It puts a lot of stress on the data and could, in the limit, cause you to just have a terrible answer when it wasn't necessary, because the experts actually could have told you, don't do that. So do you find that is there like a push-pull there, or do you already feel like, no, just follow the experts because you're always going to be better off that way?
So it's good to talk to the experts to at least know the data that you're getting is coming from which part of the distribution, right? And unfortunately, like from my perspective, the machine learning people, they don't really question the data too much, right? So there is a process that's generating this data, right? If that process has a distribution over however many dimensions, which part of that distribution am I getting the data from? And in fact, I feel like that's one of the problems in terms of how hard it is to reproduce something from machine learning. Yes, there's a hyperparameters and all that kind of stuff, but also perhaps the data I have, even though the problem is the same problem, is from a different part of the distribution and you just happen not to check, right? And then your machine learning algorithm doesn't do well on the part of the distribution that it never saw, right? So there are these assumptions that we make. So talking to the experts is very helpful. And in fact, within network science, we have all these things called the random graph models. So Erdős-Rényi is a famous one. Barabarsi-Alver is another one in terms of preferential attachment. That you can then.
So hang on. So these are different processes
for
building up a graph by adding edges.
Yep.
All randomly, but different randomly.
Randomly, exactly. And so.
And Erdős-Rényi is what?
Each edge is independent of all the other edges, I think.
So
you flip a coin.
You pick all pairs of nodes and have a uniform probability of putting in the edge. That's
and there are two ways of representing it. There's the GNP where you say, okay, I have N 100 people. No. N is the number of nodes. P is the probability of a node connecting to another node.
I get it. Okay.
GNM, which is like N is the number of nodes and M is the number of edges. And then there are lots of these other models out there that
like the small world things.
Exactly.
Those are another one of those.
Like Watts-Sograts is. And so the good thing about those models is that you can then generate a whole bunch of networks, and then you can see, well, what happens to my machine learning algorithm if my graph doesn't have a lot of triangles. Right. And so one of the things that we found recently was that a lot of these kind of graph embedding methods, these are basically you're trying to vectorize the nodes into this, usually Euclidean space, because we love Euclidean space, though now we're moving to hyperbolic as well. But putting that aside, most of those don't work on graphs that don't have a lot of triangles. But it's because they never tested it on graphs that don't have a lot of triangles, like protein-protein interaction networks.
I mean,
go ahead.
This gets at one of my pet peeves, which maybe you can make me feel better about or just agree, that a lot of the stuff that I look at uses random graphs of various types as a sort of base case, as a sort of first example. And to me, looking at it from where I come from, it feels like random graphs are extremely unusual. They're very weird. They have all kinds of properties that the graphs I deal with don't have. So saying this thing works or does X, Y, or Z on a random graph is actually not that interesting to me. Like that, is that... I mean,
no, so
there's all these limiting averages that you can do when you know that it's random, that is specific to the fact that it's random one way or another.
Right, but the thing is, you can then isolate the processes that may be generating your data, right? So you can go for like a small world network model where it's really just looking at this notion of triangles, or you can just go for one that's looking for preferential attachment. Or there's a lot of work that has been done in terms of here's a random graph model that is faithful to what I'm seeing in real life, right? So one of them is like block 2 level Erdős-Rényi. Like there's lots of these. There's the Kronecker graph model that Yuri Leskovich did. So there's a lot of work that's been put in to how do you come up with a random graph model that generates graphs that are faithful to the real world graphs that I'm seeing. In particular, social networks.
Okay, so it's not just the Erdős-Rényi, which is very weird in a lot of real-world graphs are not like that, but as a result, people have made this whole procession of different kinds of shaped randomness that have certain distributions of high-order and low-order nodes and blah, 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 like that. And then the part of the researcher effort is to say, well, for my little pile of data, hand cancer or something like that, then this kind of model is right. And is that just pull it out of your butt, or is there some algorithm for testing all random models and deciding which one to pick? How is that done?
There are usually a handful that are very popular that people use, and that's tied to the processes that you believe are generating your data. Again, this goes back to like maybe thinking more like a physicist or a social scientist that thinks about what is the process that's generating this data. So when I was at Rutgers, I had a postdoc that was a social scientist, and I remember her coming to my office and saying, Tina, these are people, they have hearts and minds. And I'm like, no. They're hashed ID in this matrix that I'm going to factorize, and I'm going to tell you what's in it. And in fact, for privacy reasons, I don't need to know about their hearts and minds. And she was like, no. You need to know, like, how this data was collected, what are these people, the sampling biases, and all that other kinds of stuff. And so thinking about how your data is being generated is useful, because then you can use one of these random graph models to test, to in a way stress test your algorithm. So one of them, for example, you would give the degree distribution. So degree is number of neighbors that you have, and triangle distribution in your graph. And then it will generate random graphs that are similar to that. Right? And then you could tweak it. You say, okay, well, if my degree distribution wasn't exactly like this, what would happen? For example, in Facebook, you can't have more than 5,000 friends as a person. So that doesn't have the kind of degree distribution that we normally think about, because it's truncated. If you're a page, you can have more than 5,000.
So if I have a graph which is like a checkerboard, the lines on the checkerboard, is that correct? It has 0 triangles?
Right,
because they're all squares.
Yeah, exactly.
Like that. So that'll be weird in terms of triangles.
In fact, it's the forbidden rectangle in social networks. People like John Kleinberg, Johan Ugander have looked at that in terms of subgraph frequencies in like Facebook network, and those things rarely happen. And there's some other interesting things. So if you find 2 people that have a lot of common friends, but they're not friends, then you can infer that they really didn't want to be friends.
Yeah, they got divorced.
Yeah, they had lots of opportunities to become friends, but they chose not to. So that's a good signal to have.
That's interesting. You can find intentionality in these lines that are repelled away like that.
Indeed.
All right. So I like the emphasis on processes and figure out the underlying process. And so when we get to something like, well, I'm going to do machine learning from head shape to probability of being a criminal, then that's where and what is your actual process, generative process that's supposed to account for that data, supposed to come from? That.
I mean, when after 9/11 happened, I was working on some of the data with Homeland Security people, and They had a node called United States. Everybody was connected through United States. That doesn't make sense. Or Robert Fisk, who was the first Western reporter to interview Osama bin Laden, came to Berkeley at the time. I was living in the Bay Area. I attended his talk, and afterwards I was in a small reception with him. I spoke with him. So now I'm connected to Robert Fisk. He was connected to Osama bin Laden. Now you're talking to me. But that's not interesting, right? Because Robert Fisk is a reporter, and or was a reporter. He recently passed. He talks to lots of people. So that connection is not interesting, versus if the connection was through, for example, Osama bin Laden's sister, maybe that would be different, right? And so there's lots of these kinds of relational dependencies or structures, which is important. And it's important to know what processes are forming these things, that there are reporters that go around. And so you're going to have these hubs, and these hubs won't have as many triangles, and so on and so forth.
But it could be a spy reporter.
It could be.
It could be.
It could be.
It'd be a good cover.
It's hard to. So with social networks or complex networks, it's very easy to fish people out because the relational dependencies are really powerful. So yeah.
Well, I mean, back in the 9/11 time, wasn't there this whole like they could go like 4 hops from anybody that was talking to an international agent, and they could like tap their phones and things like that. So you could have been tapped by being 2 hops away through the reporter.
I think that was her point. Yeah,
exactly. So knowing the processes that are generating the data is extremely important.
Well, but that didn't. The fact that we knew that guy was a reporter didn't get used to not tap your phone, because it was just too easy to tap your phone, and it's 4 hops.
But it should have been. It should. In fact, one of the resurgences of network science as a discipline, which is this interdisciplinary field, was after 9/11, where everybody was like, if we could have only connected the dots, right? Connecting the dots means form the network, form the graph. Exactly. Right. Okay,
so this is a very natural transition to your other interest in terms of, I don't know, socially responsible computing, because it sounds like maybe that's how you would get into it, is this notion that, it's a graph or it's a matrix or it's a stochastic process, but it's people. And the fact that it's people is actually important to people. And so how did you come to start thinking about those kinds of questions, and where are you now?
Yeah. So a couple of years ago, my friend Daniel Allen asked me to go give a public lecture at Harvard about AI ethics and said, talk about anything you want. I'm like, okay, I'll talk about sexist, racist robots. And so this whole thing started from there.
Wait, that doesn't sound like a starting place. How did you get to sexist, racist robots?
Well, because if you think about AI ethics, right, it's a very broad area.
Sure.
Right? You have from like super intelligence singularity to smart weapons, to security, to wealth inequality. And so I started thinking about algorithms that are being used to make high-stakes decisions about people. And that also then led me to think about democracy in general and how democracy is a complex system. And
is it a graph, though?
It is a graph. It is a graph. Everything's a graph, Michael.
Everything's a graph.
Everything is a graph. Think about it. With spectral clustering, you're making a graph. So, everything is a graph. And I mean, in terms of the AI ethics, it's very interesting in that people think they can have technical solutions to social problems. And how you hear this stuff about, well, the algorithm is more accurate or in some way. And it's like, my reaction is, okay, good. You read one study. Right? There's not a lot of details behind how the machine was put together, how it was trained, so how is it being maintained. And especially in like criminal justice, it seems like the algorithms that are being pushed, like the Compass algorithm by North Point, or the public safety assessment tool by the Arnold Foundation, these things are being treated as expert witnesses, but they're not being cross-examined as expert witnesses. And in particular, one of my pet peeves is that these algorithms do not convey their uncertainty. And so the judge sees a number from 1 to 10, 8 is bad because it's close to 10, 10 is the worst. And the guy doesn't get bail. In fact, the judge overturns the plea deal that lawyers, human beings have made because the algorithm says 8. And that to me is just nuts, because we all know that the machine learning algorithms have uncertainty associated with them. So, but then how do you actually convey that uncertainty to a person who's not a data scientist or a machine learning or a data mining person is an issue.
I mean, it seems like in movies of court cases and stuff like that, and they talk about fingerprints, and they say, oh, the chance of the mistaken identity is 1 in 20 million, whatever it is like that. And I would have hoped there would have been some analogous process for the new machine learning bail jumper estimation like that. And if they can't come up with that, that's bad, right?
Indeed. Yeah. And so the fact that they're not using that should make you think, what's going on? And then recently, a book came out by Cesar Hidalgo called How Humans Judge Machines, which is very interesting in terms of his findings. So this is basically, he's looking at it from the psychology perspective, not the philosophy perspective of how humans ought to, judge machines, where humans judge other humans by their intentions, but humans judge machines by their outcome. And so what is interesting is that they don't think that the machine was created by some humans, and maybe those humans have intentions, but it seems like the machine basically, is putting the human aside, right? It's like blocking the humans that created it.
It's intention laundering. That's what the machine does. Run it through a machine and then objective.
Exactly.
Like that. Now, is that just because it's new? I mean, are we going to figure this out, and lawyers and defense attorneys and so on will start challenging this stuff? And or is it something deeper or more fundamental, or what should we do?
I think as it goes through the courts, we will figure some of it out. I think the FDA is way ahead of any other organization in the US in terms of machine learning being used in the products that it has control over.
FDA, the Food and Drug. Okay.
Indeed, because they also deal with like medical devices and so on and so forth. So they're coming up with like good machine learning practices, the same way you have good clinical practices, good manufacturing practices. And I think they're ahead because people have successfully sued drug companies and collected lots of money, as opposed to other branches of our society.
I need more suing.
Yeah,
exactly.
And those suits were decided by judges who were following the algorithms. The algorithms really have a chance to work the system here.
Mm-hmm. Get both sides coming and going.
Exactly. It's like, you should rule in my favor.
Yeah. And the point is, you don't know the incentives of the human that is using the algorithm, right? So none of that is captured actually in the algorithm. The algorithm sees like 30 years worth of data and makes a decision, which is just horrible because over 30 years, our laws and policies change. Also, again, this is another plug for talking with experts. When I was looking at Compass, the software that was being used, so one of the counties that it was being used is a county in Florida. And I was talking to a friend of mine that's a criminologist, and he was saying, well, in that county, if you're in jail or prison, they don't allow you to renew your license. And so now you're in Florida, there's no public transportation, you're driving, and you happen to be a person of color. You're more likely to get stopped. And if you get stopped and you don't have a driver's license, that breaks the condition of your parole. And so if you're thinking about having an algorithm that could predict recidivism, perhaps you should take the whole DMV-related offenses aside, because there are these kinds of societal processes that are against certain groups of people.
So you were also, well, or at least Michael was bringing it up, that graph theory of democracy or something like that.
Yeah.
What this sounds like something I'm very, very interested in, but I don't know how to make it march. And so how do you think about that?
Yeah, so the way we were thinking about this actually started from a workshop a couple of years ago at Bristol, University of Bristol, where my friend Caroline Wiesner brought together a whole bunch of interdisciplinary people. And the idea was to think about democracy as a complex system, and then think about the democratic backsliding that we're seeing here in Turkey and Hungary and elsewhere as instability of that complex system. And so then the question is, what is stability in your field? right? Because the way that computer scientists think about stability may be different than the way physicists think about stability. And there are certain terms like stability, robustness, and resilience that are oftentimes used interchangeably. And so a lot of the experience was, okay, well, what is stability to you again? And how would this translate to democracy again? And so one of the things that we did was thinking about stability in terms of democracy in this complex system as stability over time, right? Stability of people who are eligible to be able to vote, right? And not have voter suppression. And so then if you think about democracy as a complex system, then you can study it in terms of the features of a complex system. So the World Wide Web is a complex system. In complex systems, you have randomness. Randomness is an essential feature of a democracy. Because if you get stuck in with a bad idea, it will get you out of there. The randomness will get you out of there. The problem is if you have too much randomness, then your norms break. When your norms break, as we saw in the previous administration, then people get they're more susceptible to demagogues. Look, the system doesn't work anyway. The system doesn't work for me. In fact, the use of algorithms is one of those things. If an algorithm is being used and it's not treating you well, if it doesn't see your face, right, because you happen to be a dark-skinned person, they're like, okay, well, the algorithm doesn't work, the system doesn't work. And so then the question is, how do you model randomness in a democracy? At what level do you model randomness in a democracy? Then can we actually predict that we're about to have too much randomness and our norms are going to break? And then we're going to be more susceptible to demagogues. So that basically opened up a whole avenue of like really juicy problems to look at.
I mean, I wouldn't have thought the impact and effect of the previous administration was random at all. In fact, it was directed. And modeling it as a turning up of randomness seems to be going slightly in the wrong direction.
Like if you think about it in terms of some of the problems that led to the previous administration, I remember when I was working at Lawrence Livermore, so I was outside of academia for 9 years before Michael and the Department of Computer Science at Rutgers hired me as an academic. I remember before I left, I was talking to some folks in the government, and they were saying in a few years, people will get all their news from social media. And I remember laughing at them. Right. But which of course they were right and I was wrong. But the idea is that now you may not think this is random, but now with the echo chambers, right, you get your news from only one source, right? These kinds of filter bubbles that they talk about. So then you think there's this consensus and that there nobody else who may have a different kind of opinion. So then basically you're thinking there's no diversity. Now, diversity is, again, extremely important to a democracy the same way as randomness. In fact, they go in a way hand in hand because with diversity, you get added randomness. And so there's more to it than just like, oh, this was all planned kind of a thing.
Sure. I wouldn't grant that much intelligence and agency, but there's also just a sense of, anything that goes in this direction is good for us, so we can kind of wing it. I mean, one of the things that I think about that I would like to have graph theory help out with democracy is to identify non-authentic actors, to identify astroturfing and all that stuff by somehow saying, no, sorry, that's just all Koch brothers, like that. So we're going to count them as one, that entire thing and so forth. Because I'm worried that the whole basis of one man, one vote, one person, one vote, that is a shifting sand. You can lose faith in that. And then democracy is in kind of big trouble at that point.
Yeah, in fact, so there's this whole area in computer science now called mechanistic design for social good, where people are looking at different forms of voting, right?
We've talked to some folks.
And it's like, maybe not. Maybe I don't want to have like quadratic voting or liquid democracy, or for example, now people really like sortition or these citizen assemblies, which is basically randomly have a jury that comes together and makes it, looks at a problem and sheds a light on it. This is in fact how abortion became legal in Ireland, which is a very, very conservative country. But the issue is that people are veering toward those because the representative democracy isn't doing a good job, right?
So authoritarianism is another thing that one could veer toward.
Absolutely, absolutely.
Like that. Although, if we were modeling for stability, I would think authoritarianism would be a good place to go for looking for stability. So it can't be just a self-evident good.
So you raise a really good point. In fact, at the end of that Bristol workshop, we had a thought experiment that if you were to mathematically model a democracy with just one parameter, right, what would that be? And it was very interesting in terms of what people would say. A lot of it had to say with their background, like how they grew up, right? So some were like rule of law, but in a dictatorship, there's also rule of law, right? The law is the law of the dictator, right? And so depending on what is the most important feature of a democracy to a person, that was really interesting. So the other thing, for example, for us is feedback, right? So there's the randomness that gets too much, and then your norms start breaking down. There's the diversity, and there's the feedback that we see between the politician, the media, whether it's social media or the mainstream media, and the people, right? And so then it goes in a circle. And so sometimes you need to have some shock to that feedback to break it apart. And part of that is, for example, now we have no one person that you would say, okay, that person is the most trusted man in America, right? Or woman in America. Yeah. I remember in the 60s, right? It was, I wasn't born, but my dad would say he would actually go home from his lab. He was a PhD student to listen to Walter Cronkite. He was the most trusted man in America. Yeah. We don't have that now.
Yeah, absolutely.
So.
Wow. Yeah. And I mean, I would think, in principle, one of the features of democracy is that, but you hold a vote and change all the rules. So the dynamics could just go wham by holding a vote and happening to win like
so, that. Yeah. So then there's different shades of democracy, right? So if you're thinking about it from a complex systems perspective, then you're thinking, okay, which democracy I'm modeling? So our democracy is clearly flawed in America, as opposed to perhaps other democracies in Switzerland or Norway or others. So.
Is there an accepted ranking of democracies? I don't know.
So actually, The Economist has an index where they call it, I'm going to find it over here. In fact, I had it. So the economics index, it's called the Democracy Index, in fact. Okay. And so they judge it based on civil liberties, political culture, political participation, the functioning of government, and the electoral process. And they do this over time.
I see.
And so, for example, it's between 0 and 10, 0 being worst, 10 being the best. And Norway is always on the top. We're somewhere around 8. North Korea is about 1.
As a democracy.
As measured by their democracy index. The features I just said.
Got it.
Yeah.
Got it. Okay.
And you can see the downward trend as they measure it. And you can go deep into their indices and see what they're measuring.
Right. I want the rule of law, and I want everybody who can understand the rules gets an equal shot at the franchise. And that's what authoritarianism typically doesn't provide. It's because the big man gets, 10% of everything and everybody else gets the spoils, like that. So, rule of law and equal access to the franchise seems to me to be my number one thing that would actually make it a democracy. But how to model what's going to happen once you have that.
Right. So I think those are very good ones. I think this notion of, for example, our previous president saying, I can kill somebody, right, in the middle of Fifth Avenue and nothing happens to me, that shouldn't be, right? That doesn't make sense from a democracy perspective. The other very popular parameter was freedom of speech in particular for the people who grew up in countries that they didn't have freedom of speech, that if you would say something, you would find yourself in jail. Well, it's like freedom of speech was number one.
If you don't have it, it's really important. If you get it and discover that doesn't mean freedom of audience, then it's another problem.
Indeed. Indeed.
Wow.
So, really fun things.
Well, this is terrific.
Is there a next step? Is there an action item? Is there something we can take away to make democracy better, or to demand that graphs do this? Any thoughts?
So I think thinking about democracy, whatever democracy you live in, as a complex system, and looking at the different features of a complex system, and then being able to explain what is happening through that lens is very useful, because then you can come up with policy recommendations. In fact, that is what we had done. Now, of course, ours was just one study. This is a big area to look at, but trying to understand what is going on, and not just say, oh, well, it's Facebook's fault, or it's Twitter's fault, right? But actually study it in depth is interesting and worthwhile.
Cool. I still don't know exactly what to do about it, but I feel like there's kindred souls out there, and that's a good thing.
I think step one is to understand what's happening, right? And then step two, we'll see if we can make it better.
So Tina, what's that word that comes up in data on graphs a lot, where basically nodes that are connected or indirectly connected tend to have similar properties?
So
like the birds of a feather kind of thing.
Right. So there's one is, it's called homophily.
Homophily. That's what I was feeling like. So we have homophily, right? Because we're kind of on the same side here.
Yeah. And in fact, if you have a social network and you want to find out something about a person, homophily is a very strong property. So if you just look at like Tina's friends and take the average of them, you get very close to what Tina is. So
to my takeaway then, Dave, is that we should be trying to be friends with more people, right? Apparently up to 5,000. But the point is that, or maybe 200, but because that's how we come to share views, right? And that's how we come to kind of have a perspective that says, we want this to work, and we want this to work together, as opposed to fracturing into these little sub-communities that are now going to go at each other. And I don't know, humans are good at getting themselves worked up and starting to make war and stuff. So the more we can share our views and try to talk about them intelligently and civilly, that seems important.
No, it seems good to me. So I guess we've got a homophilous triangle right here, and we want to add edges to it. We want to grow out, and that sounds like as good a goal as I can think of.
Indeed. So bringing in people from different backgrounds. So I know, for example, nowadays, diversity, inclusion, and equity is something that's talked about all the time, but those are really good things. You know, people like Scott Page have looked at it in terms of team building and how having diversity actually helps the team's performance. And this is at every scale, right? So it is good to look at things from different perspectives.
Beautiful. Well, Tina, thanks so much for talking to us. Again, I apologize for having missed our first time out, but I feel like this was great. This was a lot of fun. Thank you.
Thank you. I enjoyed this discussion.
This was Computing Up. Thanks for listening.